Let us see the Taylor series expansion of an analytic function f of z. Here let us consider a function f of z which is analytic at all points inside a circle C with its center at A and radius r. Then we can expand f of z as f of z is equal to f of a plus f dash of a by 1 factorial into z minus a plus f double dash of a by 2 factorial into z minus a whole square. It goes on like this. This fn of a is nothing but nth order derivative of f at the point A. So this is the nth term fn of a by n factorial into z minus a whole power n. It goes on up to infinity. So this is the expanded form. If we want to write it in the shortest form also, we can use summation. So f of z is equal to summation n varies from 0 to infinity z minus a whole power n by n factorial into fn of a. That is this term. Okay, if we want to write it in the summation form, we can write it like this. And if we put n is equal to 0, we will get the first term. And if we put n is equal to 1, we will get the second term, and it goes on like this. So we can use this formula to expand an analytic function as a Taylor series. So before expanding it, or before moving to the problem, here we want to notice two formulas. What are the two formulas is 1 plus x whole power minus 1, that is this is binomial expansion of 1 plus x whole power minus 1 and 1 minus x whole power minus 1. And these are the two expansion for the given term, and this expansion is valid only if modulus of x less than 1. So while using this binomial expansion while doing the problem, we have to check the condition whether the x value is less than 1 or not. It should be less than 1. Now let us see the problem. First question is expand cos z about z is equal to 0 as a Taylor series. Now we want to expand this function cos z as a Taylor series expansion about the point z equal to 0. So as we saw in the formula, that we have mentioned the formula in terms of a, that is a is the center of the circle. So here in place of a, we have to consider it to be 0. So now first let us consider the given function as f of z, that is cos z as f of z. Now we know the Taylor series expansion. For that we want to consider the successive derivatives. So the first order derivative, let us find. Differentiation of cos z is minus sin z. Similarly f double dash of z is, again we have to differentiate it. So differentiation of sin z is cos z. Already minus is here, so we have to write minus cos z. So f triple dash of z is cos z differentiation is minus sin z. Already one minus is here, so it becomes plus sin z. Similarly, fourth order derivative of f of z is cos z. It goes on like this, right? We can extend it. So at least 3 to 4 terms we can find. It's enough to use it in the Taylor series expansion. Now we have to find out the points of this given function at z is equal to 0, because it is given that we have to expand it as a Taylor series expansion about the point z equal to 0. So let us put z is equal to 0 in these functions. So it gives you f of 0 is equal to cos 0 is 1. Similarly, f dash of 0 is sin 0 is 0. F double dash of 0 is minus 1. F triple dash of 0 is sin 0 is again 0. Again f fourth order derivative of 0 is again 1. Again it goes on like this. Now we have to substitute these points in the given formula. Now if we notice, this is a formula to expand it as a Taylor series. So now here the given function is cos z, which is equal to f of a. A takes the value 0 here, so that it becomes f of 0. So what is f of 0? F of 0 is equal to 1. So 1 plus what is f dash of 0? F dash of 0 is 0 here. So 0 by 1 factorial into z minus a. Sorry, not z minus a, it should be z minus 0. Plus again this will become minus 1, because f double dash is minus 1 divided by 2 factorial into z minus 0 whole square. Next will be 0, because triple dash it is 0. So 0 into anything 0, we can make it as 0. Again for fourth term, fourth order derivative, it becomes f fourth order derivative of 0 by, it becomes 4 factorial into z minus 0 whole power 4 plus etc. It goes on like this, right? So now what happened here is we can simplify this. So first term will become 1, second term 0 into anything 0. So here it becomes minus 1 by 2 factorial into z square. Again third term 0. Next 1 by 4 factorial into z power 4. Next it should be minus, so it goes on like this. Okay, if we want to find, we can find two more terms also. Actually, obviously here the fifth order derivative will become 0 again. Again for sixth order derivative it becomes cos, that is cos becomes sine, again sine becomes cos. Okay, so that according to that we can substitute the value and we can extend the term. So this is the Taylor series expansion for the function cos z about the point z equal to 0. So if the point is z equal to 0 means we will be getting the expansion in terms of z. If it is z equal to some other point, for example a, then your expansion will be in terms of z minus a. Now let us see the second question. Here let us take f of z is equal to 1 by z minus 1 into z minus 2. So here we need to expand this function as a Taylor series about the point 1, because here it is given that z minus 1 instead of z. So which should be valid in this given region. So for this we can't able to use by the usual technique by applying it in the formula by finding the successive derivatives, because while finding the successive derivatives it will be complicated to find these higher order derivatives. So what we can do here is we can use the binomial expansion. Before using binomial expansion we need to split it into partial fraction. So let us split this function as partial fraction. So we can split it like this, plus b by z minus 2. So while splitting it, we can write like this, so that 1 is equal to a into z minus 2 plus b into z minus 1. So by putting z is equal to 2, we obtain b as 1. Similarly, by putting z is equal to 1, we obtain a as minus 1. So we can substitute here. So the given function f of z can be written as minus 1 by z minus 1 plus 1 by z minus 2. Clear? So now we have to use binomial expansion here. Before using this, we can take z minus 1 as u, because we have to do the expansion which is valid in the region 0. This is what given in the question, 0 less than modulus of z minus 1 less than 1. So this z minus 1 can be replaced as u. So z minus 2 can be written as u minus 1, because here we need what is z minus 2. So in place of z minus 1 and z minus 2, we can replace it as u and u minus 1. So this is equal to minus 1 by u plus this becomes 1 by u minus 1. So we can also write it like this, minus 1 by, we can write it as 1 minus u. Now we can take that term to the numerator and we can use binomial expansion. When we can use binomial expansion, then here u should be less than 1. So here if you notice from this, we can write 0 less than modulus of u less than 1. So which means that modulus of u is less than 1. So we can use binomial expansion to this term. So this is equal to 1 by u minus, now we can use the binomial expansion since both the terms are minus, same sign, it becomes all positive. So u square plus u cube plus etc. So now finally we need the answer in terms of z. So now finally we can replace u as z minus 1. So here it becomes minus 1 by z minus 1 minus of 1 plus z minus 1 plus z minus 1 whole square plus z minus 1 whole cube. It goes on like this, right? So this is the expansion of the function f of z about the point 1, or which is valid in 0 less than modulus of z minus 1 less than 1. Now let us see the statement of Laurent series. Statement of Laurent series is if a function f of z is analytic on two concentric circles C1, C2, whereas in Taylor series we will be taking only one circle, but here we have to take two concentric circles C1 and C2. That is, here we have to take one circle and then another circle. Okay, so this is let us consider this is to be the circle C1, this is to be the circle C2, and this is radius R1, small r1, and this is the radius R2. Okay, like this we have to take, and the annular region, that is here the center point is considered as A, and the annular region, and also on the annular region R means this in between region is called as annular region. Okay, so this region is called as annular region. That is, we have to expand the given function as a Taylor series in the annular region, that is which is analytic at all points in the annular region. Okay, which means that actually here may be some points inside this circle C1 where the function may not be analytic. So omitting this point, we are considering the remaining region. Okay, so that is what the reason we are going for Laurent series. So what is a Laurent series expansion is, here this is a expansion for Laurent series, that is f of z is equal to summation n varies from 0 to infinity a n z minus a whole power n plus summation n varies from 1 to infinity b n by z minus a whole power n, where a n and b n, this a n and this b n is defined like this, and both the integrals being taken along anti-clockwise direction. Okay, so this is the Laurent series expansion. That is, if you notice in the Laurent series expansion, the expansion contains both positive power of z as well as negative power of z. So this first term expansion will give you positive term of z, and the second term of the expansion gives you the negative term of z, whereas in Taylor series all the terms will be positive terms, that is all will be in powers of positive powers of z. Okay, so this is the statement of Taylor series. And here this first part is called as regular part, and the second part is called as principal part of the Laurent series. See the third question. Find the Laurent series expansion for f of z is equal to z minus 1 by z minus 2 into z minus 3 in the region. Here it is given three different region, modulus of z less than 2 and 2 less than modulus of z less than 3 and modulus of z greater than 3. So again here let us consider f of z is equal to the given function z minus 1 divided by z minus 2 into z minus 3. So what we did in the previous problem, the same thing we have to do. We have to split it into partial fraction. So this can be written as a by z minus 2 plus b by z minus 3. So z minus 1 can be written as like this. Now we have to put z is equal to 3 to get b value. Similarly, z is equal to 2 to get a value. So if we put here, we get the values of a as minus 1 and the value of b is 2 plus 2. So here the given function f of z can be written as a is minus 1, that is minus 1 by z minus 2 plus b is 2, so 2 divided by z minus 3. So now as usual we have to expand this function as a binomial expansion. For that we have to take it to the numerator before expanding it. So before that, first let us take the first subdivision. So how to use the binomial expansion? Here we have to give three different expansion according to the region given. So first is the region modulus of z less than 2. So modulus of z less than 2 is nothing but 2 is also less than 3. Why we are taking additionally this number 3 is here we are having one more term z minus 3. So that we have to check this. So this can be written as two different terms, that is one we can take modulus of z less than 2 and another we can take modulus of z less than 3 also. So from this we have to bring it as less than 1. When it becomes less than 1 we have to divide both the sides by 2. So modulus of z by 2 can be written as less than 1. Similarly here modulus of z by 3 can be written as less than 1. So while using binomial expansion to this term, we have to expand it or use binomial expansion in terms of z by 2. Similarly z by 3. So now we have to write these two linear factors in terms of z by 2 as well as here z by 3. When we can do like this can be written by taking 2 outside. Clear? So what we can do here is, if you notice this f of z can be written as minus 1 by, if we want to take 2 outside, first we have to write it like this, minus of 2 minus z we can write. Similarly plus 2 divided by, here if we take minus outside we can write 3 minus z. Clear? Now this can be written as minus into minus plus. Here now we can take 2 outside, so this becomes 1 by z by 2. Similarly here minus is here, so we can write 2 divided by 3 we can take outside, we can write it as 1 by z by 3. Now again we can write 1 by 2 as a common term and then we can take the denominator to the numerator as negative power. Similarly second term we can write 2 by 3 into 1 minus z by 3 whole power minus 1. Now we can use binomial expansion for these two terms. Why we can go for binomial expansion? Because in place of x we are having z by 2 which is less than 1. Similarly here z by 3 which is less than 1. So now clearly we can use, without any doubt we can use binomial expansion, so that here both are of same sign, all positive. So z by 2, z by 2 whole square, z by 2 whole cube, it goes on like this, etc. Similarly for the second term, 1 plus z by 3 plus z by 3 whole square plus whole cube, it goes on like this. So this is the Laurent series expansion of the given function which is valid in modulus of z less than 2. That is, this is the expansion which is valid in modulus of z less than 2. This is the first subdivision. Now the second subdivision is 2 less than modulus of z less than 3. So now how to bring it as less than 1? First 2 less than modulus of z and modulus of z less than 3. So from this 2 by z will be less than 1, whereas here z by 3 will be less than 1. So you can notice the difference here. Here we have to divide throughout by z, modulus of z. Here we have to divide throughout by 3. Okay, both the sides. So that anyway we have to bring it in the form of less than 1. Then only we can apply binomial expansion. So again here f of z is equal to, already we know the term is minus 1 by z minus 2 plus 2 by z minus 3. So now what we have to do here in the denominator, we have to take z common here, then only we will be getting it as 2 by z. But here we have to take 3 outside. So here we can keep z minus 2 as it is, whereas here we can take minus 3 common and we can write it as 3 minus z, then only we can take 3 outside. So this can be written as minus 1 by, now you take z from this, which we can write 1 minus 2 by z minus 2 by 3 into here, sorry, here it is not 3, just we have taken minus 2. So that what happened here is by taking 3 outside, it becomes 1 minus z by 3. Clear? So from this it becomes 2 by z. Because of this, here we have taken z by 3. So now this can be written as minus 1 by z into 1 minus 2 by z whole power minus 1. Here 2 by 3 into 1 minus z by 3 whole power minus 1. Now we have to expand it. So minus 1 by z into the expansion is plus 2 by z whole square plus whole cube, etc. Again here 2 by 3 is common. So 1 plus z by 3 plus z by 3 whole square, etc. So this is the expansion of f of z, which is valid in 2 less than modulus of z less than 3, right? So the term f of z is the same thing after partial fraction. We are using the same term, but the only thing is according to the region we have to modify the term before using what? Binomial expansion. Now the third region is modulus of z greater than 3. So because of this, 3 is also greater than 2. Clear? So from this, modulus of z greater than 3 and modulus of z greater than 2 we can write. So anyway we have to bring it as less than 1. So this becomes 3 by z less than 1 because we have to throw divide by z. And here again 2 by z will be less than 1. Clear? So in both the case or both the terms we have to take z common. Okay. So here this is z minus 2 plus 2 by z minus 3. So this is the term. So from this we can take z common, so that this becomes 1 minus 2 by z plus 2 by, we can take again z common, so it becomes 1 minus 3 by z. Now we can easily apply the binomial expansion. Is it clear? So this becomes, so here it is 3 by z, so we have brought it in the term of 3 by z. Here it is 2 by z, so here it is 2 by z. Now without any doubt we can use binomial expansion. So this is whole square, it goes on like this, plus again 2 by z into 1 plus 3 by z plus 3 by z whole square, it goes on like this. So this is the Laurent series expansion of f of z, which is valid in modulus of z greater than 3. So question, the function is the same function, but we have given 3 different expansion depending upon the 3 different region. So this is the way we have to expand the given function as a Taylor's series and Laurent series.